In this video, we are going to go over how to create these load versus displacement plots that we have in this example, post-buckling of an imperfect cylindrical shell. This is going to be part 2 in this video series. In the first video, I'll walk you through how to set up a linear buckling, post-buckling, and a nonlinear buckling analysis. But one thing I did not cover in that first video, I did not cover how to create these load versus displacement plots. Also, the documentation, this example doesn't really tell you, it doesn't explicitly tell you how these plots were generated. So in this video, I want to walk you through how I think these plots were created. So for those who do have a question of how in the world was this plot created, hopefully this video helps answer this question. How was this plot created? Okay, now this is what I'm assuming. These plots were created based on the following. So here in this example, they use mode 4 to define a geometric imperfections. They actually use mode 4 to describe 1, 2, 3, 4, 5, and 6 geometric imperfections. They use that data to create the first blue, pink, green, turquoise, brown, red curves. So here 1, 2, 3, 4, 5, 6. So again, those first 5 plots, traces, lines, they were based on the geometric imperfections based on mode 4. Now for the last line, the orange dashed line, that was using the geometric imperfection here that consider all 16 buckling shapes. So this data is going to be contained in the following examples or bulk data files. This file, cylinder version 2, this is going to consider mode 4 6 times. And then the last file, this file is going to contain modes 1 through 16, one geometric imperfection. And then so here we have 6 geometric imperfections. So I'm assuming you already know how to configure these files, or you know how to get access to these files. If you click on this file, if you click on that, this will open your web browser, and then it's going to download the bulk data file for you. Okay, now once you download those bulk data files, run the bulk data files. When you run those bulk data files, you get these H5 files. So it's in these H5 files, we're going to extract data to build these plots, the load versus displacement plots. So let's go ahead and get started with how to create these plots. Okay, so first, let's go ahead and look at the viewer. So here we've uploaded one of those bulk data files. Let's go ahead and turn on the LBCs. Let's adjust the size of the arrows. Let's use an arrow size of 60. So if we're using units of millimeters, the arrow length has units of millimeters. So in this case, the arrows are 60 millimeters in length. I increase the size so the arrows are visible. So here you can see the arrows for the forces, and you can see arrows for the boundary conditions. So here it's fully fixed. And then at the top, we only allow translation in the Z degree of freedom. So there's no Z restriction here. So we have this configured in a way that allows for axial deformation, if you will. So here we need to identify these node numbers. So there's one way of doing this. Let me see. There's an easier way of doing this. Okay, so there's actually an easier way. So the very difficult way of doing this, let's go ahead and hide everything. The difficult way of doing this is, or let me take a step back. I want to determine every ID, every node ID where there's load applied. So I want to know what this node is, and so on and so on. You can go to the Fem label tool and select all these individual nodes, which is possible, but that might be a little tedious. So here, let me show you how to do that. So we'll go ahead and select this node, and we'll just go ahead and do this again and again. Here, we'll turn off the display labels option. But you can see this is going to be a little tedious. Let me turn off the arrows also. So you can see this is going to be tedious if we have to go around the entire cylinder. And that's what I did earlier when I was practicing this exercise. But there's a much faster way. We know we want all the nodes that have a force entry. If we go to this table, force entry, all the nodes that were used are listed here. So let's go ahead and copy those nodes for now. We'll come back to these node IDs later on. Node or grid IDs, grid/node IDs that are loaded with force entries. So we'll come back to this list later on. Okay, now, assuming you have the H5 files, let's jump over to Windows. Now, one thing I forgot to comment, we are going to be using a web browser to help us create these plots. If you want to follow along with this exercise, you want to use these web applications, you can visit theengineeringlab.com. Top right hand corner is a blue button for a free trial. Click that button, fill out the form, and we'll go ahead and give you access to these web apps. So once you get access to the web app, you want to open what's called the HDF5 Explorer. So the HDF5 Explorer can be used to create all these different plots. Now, let me do one thing here. Let me relocate these files. So you have a few options here. You can upload the H5 file directly. Here, that could work really well, but suppose your H5 file is 10 gigabytes big. Then you have to wait for who knows how long, maybe 5 minutes, 2 minutes to upload a 1 gigabyte or 5 gigabyte file. So there's an alternative upload option. Switch the option to B, broadcast, click on full instructions. Read through the instructions, follow the instructions. And so what this will do, it will download a small executable file. Let's go ahead and start broadcast app. And here, let's see if this works. I don't know if it'll work. There's a step that's missing here. Okay, so what I did here was I specified the session ID. So in step 4, you get a session ID. Take that session ID. It's going to vary depending on the device. Every time you reload the page, the session ID changes. So this is a unique number. It's going to be different for you. I took that number, I submitted it, and then let's see if the window's still here. I get asked to select an H5 file. So let's go ahead and select this H5 file here, V2. Select that file. And then it's going to start emitting and broadcasting that data to the HDF5 Explorer so you can see it's loaded the data. So this is a big time saver. You don't have to spend 5 or 10 minutes uploading a 50 gigabyte file. You can just use the broadcast option to save yourself some time. Okay, so let's do this. Let's do this. Let's take maybe node 52. Let's quickly create a load versus displacement plot. So here we'll say, let me go here and delete this old plot. Let's acquire the apply load for node 52 and click acquire dataset. And then here, I think there might be too many imperfections. In the select domains option, you can say only get data for this imperfection. So what happened in that bulk data file, it considered mode 4, but then it created 6 geometric imperfections. That's why we have IMPFID 1, 2, 3, 4, 5, and 6. Here I'm saying only acquire data for imperfection 1. And then this table has only data for imperfection 1. Click on create plot. And so now we have the displacement history for node 52 for imperfection 1. Let's go and repeat this for displacement. So that was the apply load that we just created. Let's do this for displacement. So we'll select a displacement here in node 52. Here in this table, we'll say do this for imperfection 1 or geometric imperfection 1. You can mark out these checkboxes one by one, or you could click this green box and it'll select all the visible checkboxes. So let's go ahead and do that for the second page, and then click on acquire data set, and we'll go ahead and create plot. And then we'll go ahead and select this for the z-axis. The z-axis is going to be the direction of the loading. So that's what we care about. We only care about deflection and load along the z-axis. Okay, so you notice that for the apply load, the component, the vertical axis is the z-axis, and then for the displacement, the z-axis. Here in the top bar, click on combine plots. For the first data set, select the apply load data set, and then for the second data set, select the displacement. So what this is going to do, it's going to combine the apply load and the displacement plot. So you'll notice right now the apply load is in terms of displacement versus time, if you will, or loading. Here, the displacement is in terms of, all right, let me repeat that. Here, the vertical axis is applied load. The horizontal axis is load step. Here, the vertical axis is displacement, but the horizontal axis is the load step. But what we want is a loading versus displacement plot. So we want to combine plots. We selected the apply load and the displacement. And now we get a load versus displacement plot. Now, this is where we catch a discrepancy. Here we see that the maximum load is 80,000. Let me confirm that's the load here. Or it's 800,000, sorry. So here the maximum load they have on the vertical axis is 800,000 newtons. But when we look at this plot, we only get 9,000 newtons. So when you try and create the load versus displacement plot using one node, it doesn't give you the same plot that you get in the documentation. So this is where I was kind of wondering, okay, how did they get this plot? Here I'm only getting a fraction of the load. So after experimenting, this is what they did. They took the load for all the nodes and they combined it. And then they took the minimum deflection for these nodes, for the same nodes, and used that. So let me walk you through with how to do that. So here, what we're going to do is the following. Let me delete all these old plots. So we're not going to use this tool to plot. What we're going to use this tool for is the following. We're going to get this table and extract it. So for the apply load, let's go ahead and type in all those node IDs. So all these nodes are the nodes where we apply the load. So we're going to click acquire data set here. Let's go ahead and make sure we selected imperfection 1 and click acquire data set. And let me go ahead and prepare my desktop here. Okay, so we clicked on acquire data set, and now all of this data are the time histories for every node for geometric imperfection 1. We'll go ahead and click on download CSV rather. And then here we've got this new file here. We'll call this applied load. And then let's go ahead and do this for, we'll copy these grid IDs. We'll do the same for displacement. And then actually, let me redo this because I think there is something off here. Okay, well, let's just go forward and see if it works. We'll select displacement. We'll use the same node IDs. And then let's go ahead and make sure that all the checkboxes for imperfection 1 are selected. Okay, we'll click on acquire data set. And then we'll go ahead and click on download CSV. And now we have a new CSV file that's been downloaded. Here we'll call this displacements. So let's open the apply load CSV file. And let me look at this. Oh, maybe I do have to create plots. Okay, so there's one step I neglected here. So let me delete the apply load data set, or apply load CSV file. Let me actually create a plot of the displacements here. So I click on create plot, and then I get a bunch of lines. And then here we'll select this, we'll set the vertical axis for the Z component of displacement. Click on view filters and plotted values. Click on download CSV. And I get a new set of traces here. We'll call this displacements. So we'll copy this, and then we'll take the minimum displacement for those nodes where we apply the load. So we'll use the minimum function, and then we'll do this for all the displacements from all the nodes. And then let's go ahead and drag this to the far right. And so we'll use these values in a moment. So let's go ahead and save this file. Let's do the same for the apply load. So we'll go ahead and switch over to apply load, select all these node IDs, and then here let's make sure all these checkboxes are marked for the first geometric imperfection. Click on acquire data set, click on create plot, and then jump over to that plot. Make sure the vertical axis is the Z axis. Go to view filters and plotted values, click on download CSV. We'll go ahead and call this traces. Oh no, sorry, apply load. Let's open that file. Here we'll do the total sum of load. And then let's go ahead and go to the very end. Okay, now we'll create a new spreadsheet. And then we'll go ahead and select this row containing the minimum axial deflections. And let's go ahead and use the paste values option. And then for apply load, we'll do the same thing. So we'll copy the apply load and then do that here. And then we'll select those two rows and go to insert. And we'll use maybe this option. So now you'll notice that this blue line is starting to resemble this line. So let's do a few things here. Let me modify this axis because they go in increments of 200,000, I believe. Okay, so let me look at this document. So for the x-axis, they go up to 8E5, so let's go ahead and modify that. So the maximum value along the vertical axis is 8 times 10 to the 5. And then let me go and see if we can use scientific notation. Okay, let me do this. Let me make these values scientific notation. And then let me change the color of this line. See if I can do that. Okay, so this line is this blue line. So you can see the blue line that we just manually created is aligning to the blue line from the documentation. So this one's going to be the no imperfection scenario. So this is a imp geom equals 1. So this is the first geometric imperfection. Imp geom 1, what does that look like? That would be this one here. Imp geom 1, so they use buckling Moche 4 with a 0 scale factor, so that's equivalent to no imperfection. Let's create the load versus displacement plot for imperfection geometry 2, which is buckling mode 4 with the scale factor 0.2. So if we look at plot, that would be this magenta or pink dashed line. So mode 4 imperfection equals 0.2 millimeters. Okay, so this is what I'll do. I'll show you how to create this one. I'll pause the video and create the other ones for 0.4, 0.6, 0.8, and 1 millimeters. And then I'll unpause the video and continue with the last one. Okay, so let's jump back here. So now let's save this for now. We'll call this zero load versus displacement. Let's close this. Let's save this. And let's save this and close this. So this is going to be imp geom 1, imp geom, imp geom 1 displacements. Okay, so let's do this for the second geometric imperfection. So let's delete these old plots so we don't get confused. It's very easy to get it confused with all these plots. So let's delete these old ones. So if you go to the plots browser, you'll see it's empty. Okay, let's go ahead and deselect all these checkboxes. So let's go ahead and acquire the apply load for all these node IDs. Here in the IMPF ID column, let's select 2. So we're getting data for the second geometric imperfection. So let's go ahead and mark all these checkboxes. Click acquire data set. Click on create plot. Click last plot added. So we jump here, make sure the vertical axis is Z. Click on view filters and plotted values. Click on download CSV. And let's rename this. This is apply load. So imp geom 2 apply load. So this is going to be the apply load for this configuration. So let's go back here. So imp geom 2, so this is buckling mode 4, the scale factor 0.2. So that's what we're doing right now. We're getting the data for that second geometric imperfection. So we got the data for apply load. Let's select displacement, submit the node IDs. Let's go ahead and uncheck everything here. Let's switch over to the second geometric imperfection. So we'll select 2 here. Mark all the visible checkboxes. Mark these checkboxes and click acquire dataset. Now, one thing you want to confirm is the following. When you click acquire dataset, here on the far right hand column, make sure IMPF ID is the one you expected. Here we expected 2, so we only get 2. If you see 1, 2, and 3, that's not correct. You want to make sure you only have 1 ID here when you're going through this procedure. Okay, so we're done here. Let's click on create plot. We'll jump to last plot added. Click on that, and we're here. Let's click on the Z component, and let's go ahead and click on view filters and plotted values. Let's click on download CSV, and let's rename this imp geom 2 displacements. Okay, let's open apply load. Let's find the total load. So we'll do the sum. Here at this point, let me think. I think the apply load will be the same for all of these. Right, 3, let's confirm. So we could save some time and just not have to recompute the apply load. Or actually, I think the load does change. Okay, so the load is different from these different versions. Okay, so we'll continue on then. So here we computed the total load for the second geometric imperfection. And now let's go ahead and do this for displacements. So for displacements, we want to know what the minimum displacement is. for the top node. So we'll equal minimum. So during the loading, for these top nodes where we apply the load, what's the minimum axial displacement? So we're using min of all these values, and then we'll go here. Okay, now let's go ahead and copy these values. We'll copy this to that main spreadsheet. So this is a, let me save this. This is imperfection with 0.2 millimeters, and this is imp geom equals 2. We'll copy the displacements here, and then let's go ahead and use the number option. So here we're saying just copy the numbers, don't copy any functions, and then we'll do that for the apply load. So we'll copy the apply load, and then we'll paste it here. And then like before, we'll select these two rows and we'll create a new plot. And then here we could do the same thing like we did before. We'll format the vertical axes. We'll make this 2 here, so we want 2 increments. We'll use scientific notation. So here what I'm doing is I want to format the plot so it looks similar to what's shown in the documentation. And then for the upper bound, we'll go ahead and make this 0.6. And then if we look at the plot, I think the plot is magenta. Yeah, it's magenta, so we'll color this a magenta color. So let's go ahead and look for magenta here. Formats. Here we'll go to color. Let's go ahead and see if we can find a magenta color. We'll use something like pink. And then we'll use dash lines. So maybe something like that. Now there's one really nice option in Excel. If you click on the white space, right click on the white space, copy, click on the white space of the second graph and paste, it's going to superimpose the 2 plots together. So that's a big time saver. So let's look at this. Here we see the peak load is about 400,000 newtons. And then that's matching with what we see here. So you see from this plot, from the documentation, the peak load is about 400,000 newtons. And then we're getting the same value here. What about the deflection? The deflection is a little over 0.3 millimeters. And then also you see the peak deflection is about 0.3, a little over 0.3 millimeters. So that's how you create the first 2 plots here. I'm going to pause the video and repeat this for an imperfection with 0.4, 0.6, 0.8, and 1 millimeters. So I'll see you after the pause. Okay, so I repeated the procedure for the other geometric imperfections 3, 4, 5, and 6. And now I'm at the part where I'm going to start combining all of this into a single plot. And the hope is that this final plot looks like the one from the documentation. Okay, so let's continue. We have geometric imperfections 1 and 2. Let's do this for 3. So let's go ahead and create a plot. Let's go ahead and copy this here. And then let's look at what color that one was. That was green, so we'll color this one green. Green, and then we'll use a dash line. And then let's go ahead and do a quick confirmation. So this is about a peak value, peak load of about 300,000 newtons. And then this is also about 300,000 newtons. Okay, so that one looks okay. Let's go ahead and delete this plot. Let's go ahead and do this for the next few plots. And I think I'm going to do this a little faster. So while doing this, I just realized that with the pace of artificial intelligence, hopefully I can just ask an AI bot to do this automatically for me. I could use Python to do this, but the time it would take to write up that Python would just take a lot longer than manually creating these graphs. So you're always having to decide, okay, do I do this manually? Do I script it? Or do I use some other approach? I'm sure there is an easier way to do this, but this is what's working for us today. Okay, this one's going to be this color, and then this color, so we can delete this one. And then we'll do this, we'll copy this here. And then what color is this one? This is going to be the brown color, I believe. So we'll color that brown, dashed. This plot looks a little different, but that's okay. This example was created, 5 years ago? So it's possible I made a mistake somewhere, or something in the Nastran code changed. And then I think that was this example. So let's go ahead and copy this one and paste it here. And then see what this one, I think it was a red color, right? So this one was red. So let's make that red and make it a dashed line. And we'll delete this. So you can see we're on the right path of recreating this plot from the documentation. All that's left to do is to create the final plot, which was for the mixed mode example. One quick comment. While doing this, it's very important that this far right hand column, it has a single imperfection ID. If you ever have two IDs, let me show you an example where there are two IDs. So here, let me check all of these. If we look at the acquired data set, you can see there are two IDs here. So you don't want this. You only want one ID, or the plots you create are going to have multiple imperfections, and then all the data is going to get messed up after that. So again, make sure there's only one ID every time you do this. Here, let's make sure we deselect all the checkboxes. So here we have all the imperfection IDs listed. Let's go ahead and go here. And then there are a lot of pages, so let's just focus on IDs 5 and 6. We know it's 5 and 6 because 5 and 6 are listed in the column on the right. So here we display 5 and 6. We unselect all the checkboxes. And once that's all been deselected, say we want imperfection ID 3, we select 3, click on mark all the checkboxes, and then click acquire data, and you'll notice that the column on the right has only one ID 3. And so here, let's deselect all these checkboxes, and let's do this for 5. Select all those checkboxes, click acquire, and now you have one ID. So keep that in mind if you're following along with this exercise. Okay, now let's go ahead and do this for the last plot, which again is the mixed mode 1 through 6, the orange dashed line. So let's go ahead and get that plot. So let's go ahead and create and open a new HDF5 Explorer. Let's use the broadcast option. Let's copy this unique ID. Let's go back to this directory and restart this broadcast executable program. Let's use that session ID. Let's pick this other H5 file, version 3. So in version 3, if you recall, is using this configuration for the geometry imperfection. So we combine all 16 modes and use the scale factor for each one. So we uploaded that H5 file here. So let's go ahead and do this. Let's go ahead and copy the node IDs that I have backed up. Click acquire dataset. Now here, we don't have to worry about the domains. We don't have to use this checkbox because there's only one ID. So we can just ignore the domains, click acquire dataset. if you confirm the IMPF ID column, there's only one ID there because we only considered one geometry imperfection in this case. Okay, so we'll click on create plot. We'll go here, z-axis, and then we'll go ahead and click on download CSV. We'll rename this one. We'll call it traces imp geom 101, just to distinguish this. Displacements. And then we'll do this for the apply load. So we'll go to, that was apply load, sorry. So apply load. And then we'll do this for displacements. And then we'll click on create plot. Last plot added. And then here we'll click on the Z axis and then download a CSV. And then we'll rename this just so we know where this data came from. We'll open the displacements, and here we'll do the same thing we've been doing a million times at this point. Take the minimum axial deflection for those nodes that we loaded, and we'll do this for every load step. We'll save this file, and for the apply load, we'll take the total. Did I do this right? Oh, I didn't do this right for the apply load. So I think what happened for the apply load was I didn't use the correct node IDs. So let's go and look at that. All right, I must have not selected the right node. So let's repeat the process for this. And then download this, and let's rename this. So like I was saying a little bit earlier, hopefully in a few years, we can just use AI to query all of this data for us. I've seen what AI can do, especially for databases and data. It's really good at acquiring specific data sets for you. Okay, let's save this. And now let's copy this row and move it over here. Let's copy that here. And we'll do that for displacements. Copy this data here also. And then this is going to be imperfection. So this is imperfection in geometry, imperfection based on mode 4 with 6 different scale factors. And then this is a geometric imperfection based on modes 1 through 16 with constant scale factor of 0.16, so on and so on and so on. Okay, now let's create a plot of this last set of data. And then we'll copy this into the main plot. Oh, something's off. Oh, yeah, something is off. So I have the rows reversed, so that's what's going on. So let me create this plot again, select these 2 rows, create this plot. Now I can copy this and hopefully it will match what's shown in the documentation. And then let's go ahead and color that line. So what I'm doing now is I've selected this line, and I want to change the color to orange and make it a dash color so it's consistent with the documentation. Okay, so let's go ahead and modify this a little bit more. So this was going to in increments of 200,000. The upper bound was 8E5 or 800,000 newtons. Okay, perfect. So let's go ahead and add some labels here. We'll go ahead and add our horizontal and a vertical axial load, and this is in newtons, and then the horizontal axis, this is a axial displacement millimeters. And then if we look back at the documentation, you'll see that it's aligning load versus displacement at the top nodes. So that's kind of subjective, or I'll delete that. So the whole goal of the video was to reproduce this plot that you see here, and you can see we've come pretty close. There are some slight differences, like this orange plot. This orange plot, if we look at this diagram, it looks like it goes up to 0.25 millimeters, and it goes up to nearly 300,000 newtons. But here, when we recreated that plot, we only went up to maybe 2.1 millimeters, and we're close to 300,000 newtons. So this plot looks like it's 95. This plot here looks like it's 95% matching what was shown in the documentation. Unfortunately, the documentation didn't tell us exactly how they created the plot, so we had to guess at how they created the plot. For load, I think for the load we were 100% accurate. It's the axial displacement where they really didn't tell us how they got that data. So what we did is we took the axial displacement for the top nodes where the load was applied. So we got the time histories for all these loaded nodes, and then we determined the minimum deflection or displacement for every load step. So if you recall, we used the min function here. We said for every node, for every load step, find the minimum, record that, and then that's what we use to create these plots. So there you have it. That's my interpretation about how they got those load versus displacement plots. So let me leave you off with one last thing. Just in case you do have a question or comment, you can contact me at this email address, and I'll try and get back to you as soon as possible. I know some of you will look at this and say, hey, I can script this. I'll go ahead and script it. Definitely. If that's a better approach, definitely go with that. For me, I realized that trying to script this would take me 2 or 3 hours, and this is a one-time script. I don't think I'll be doing this every day, unless you do. If you have to do this every day, then it makes sense to go ahead and script this. Invest the 3 or 5 hours, build your Python scripts, and then you can use the scripts every day. But for me, I'm only doing this one time, so I went ahead and manually went and built these graphs. Hopefully in the future, AI will be far enough where we can tell it, hey, AI, query the H5 file, get me this data, automatically build all these CSV files and build this final plot for me. Hopefully in the near future, that would be a possibility, but I don't think we're there yet, or at least nobody's tried. So yeah, that's how you build this plot that we found in the original example. Thank you for watching.